In this video, I'm going to talk about specific latent heat. I'm going to talk about what it is and how we can find it by both calculations and during experiments. Please take a moment to read the success criteria for this video. So let's start off with what specific latent heat is. First of all, we have two different kinds. With latent heat, we're talking about the amount of thermal energy needed going between two different states or two different phases. First of all, we could talk about the specific latent heat of fusion. That would go from a liquid to a solid. Now realize if I go from a liquid to a solid or a solid to a liquid, it's the same amount. It's just whether I add that amount of thermal energy or I remove it. Another thing that's really important is this is at a constant temperature. So if we are changing state or changing phase, for example from solid to liquid, the temperature doesn't change. If you think about water, at what temperature does ice melt? 0 degrees. At what temperature does water freeze? 0 degrees. So all the energy is not going into kinetic energy or the change in temperature, it's going to potential energy, either being able to overcome those bonds of attraction. If we're removing energy, then the bonds of attraction are able to pull the atoms or particles together into a solid, into their lattice formation. If I want to talk about liquid to gas, this is going to be vaporization. I'm also then going to have a constant temperature and pressure. An interesting fact is that pressure can have a definite effect. If you live at higher altitudes, for example, in the Rockies, in the western part of Canada and the US, then water will boil way up in the Rockies at a lower temperature. It's not at 100 degrees. This is due to a lower air pressure. And so you can actually find things on the side of like cake mixes and things that tells you how it changes the effect of cooking. So let's look at this experiment here. I have a kettle on top of a scale, and I'm going to leave the lid open and I'm going to let the kettle boil. You can see here I've measured the time, and what has happened? Well, my dots here show me that the mass of the kettle is going down. Now you should be able to understand why. With the lid being open, all of the water that's turned into steam can now leave the kettle through convection. That means I've got a record here of how much water has actually left my kettle. That would be the amount of water turned into steam. I could use my graph, you can see it's a nice straight line here, to get a value of the mass per time that left the kettle. So let's take this a little bit farther in the next slide. So now in this case, what I've got is I actually calculated the mass that was boiled away. Rather than the graph I had before, which just told me what the new mass the kettle was, now I can more specifically look at the mass of water that was turned into steam. Now, it's kind of hard to see right here, but my gradient is 0.8333. That would be grams per second. Now the equation for the latent heat is Q equals mL. And in this case I could put a little v because we are talking about vaporization, going from a liquid to a gas. I'm also having to add this in. Now I don't have the heat here. What I have is the power of my kettle. Now power is energy over time, so if I divide this right here by time, I can also divide this side right here by time. And now I have these two values. My power, the energy over time, is 2,000. That was given to me. The mass per time, that is my gradient. and then our latent heat. One thing to remember is that this was grams per second, so when I calculate my answer, it's going to be in joules per gram. If I move that around, my latent heat of vaporization, and I'm going to pick up my calculator, it'll be 2000 divided by this decimal 8333. I'm going to get 2,400 joules per gram. Now if I put that into joules per kilogram, I'm going to get 2.4 times 10 to the 6 joules per kilogram. Now the real value is 2.25 times 10 to the 6 joules per kilogram. So not that far off. One thing I want to note is that my value was larger than expected. The reason that's important is it meant that I added in more energy to change this mass of water into steam than expected. The reason that's important is, where did that extra energy go? There must have been heat loss during my experiment. Energy that I thought was going to my water to warm up probably left the kettle. So let's evaluate then if we had heat loss. The kettle is hot to touch. What does that do to our results? This is important because you don't want to give a reason why your value has some random or systematic error if it goes in the wrong direction. If I had something going on that would have predicted a smaller amount of heat, it would not have justified my value being bigger than expected. Likewise, if some steam condenses on the side or the lid and goes back into the kettle, let's think what has to happen then. In order for that mass to truly leave, I would then have to add even more energy to cause it to turn into steam one more time. One other thing about this, make sure you're very clear there's a difference between evaporation and vaporization. A common example I do in my class is I lick my hand. Now, that water will disappear due to evaporation. It is not going to vaporize. Vaporization is going to have to be at 100 degrees, thereabouts, off of my skin, which would hurt. But we all know that evaporation is what our body does when it produces sweat. That's going to cool us off. That's not painful. Evaporation happens only at the surface of a liquid. Vaporization happens throughout the liquid. So let's look at an example. Specific latent heat of vaporization of a substance is defined as the amount of thermal energy required to... Well, if you remember the units, they were joules per gram or joules per kilogram. So it's not just to change a liquid, I need the per unit mass. And does it have to be at pressure or temperature? It needs to be at a constant temperature. I had said that pressure could change the temperature it is, but that's not going to change how much to go from one state to another. Using an electric kettle, we have 150 grams of water at 100 degrees Celsius converted to steam in 400 seconds, and it gives us a specific latent heat of steam. What is the average electric power used? So let's start off with our equation for latent heat, Q equals mL. Now since I need power, that is energy over time, so over here I'm going to need over time as well. So my mass will be the mass of water. In this case, it's going to be 150. My latent heat, 2250. Notice it's in joules per gram, so I can leave this mass in grams. All over the time. The temperature isn't part of this equation. It's not part of the equation for latent heat. It is for specific heat capacity, because that's all about changing the temperature of a substance. If I look over here, You can see my answer is D. We have 100 grams of water poured into an insulating cup. Here's my cup. And we put in 50 grams of ice at 0 degrees added to the water. And we're going to stir until the temperature of the water has fallen to 0 degrees Celsius. 18 grams of the ice is unmelted. Well, the first thing we should do is we should calculate how much ice actually melted. That's important because that is the amount of ice that was used to actually reduce the temperature of the water. So if I use a conservation of energy, that means the amount of ice that was melted, and I'm just going to put little I's here for ice, is going to equal the change in temperature of the water. I'll put little W's to stand for water. Moving this around, I'm going to have the mass of water, which was 100, times the specific heat capacity of water. Notice we always have to double check there's no standard unit. Joules per gram, we've got 100 grams, that's good. Times the change in temperature. Now this will be the temperature change of the water. The water has gone from 25 degrees and it goes down to 0. So that will be 25. All over the mass of ice that was melted. Now if I pick up my calculator, I'm going to get 328 joules per gram. The real value is 334, so that's not so bad. To find the specific latent heat of fusion. The amount of thermal energy needed to convert a unit mass of a solid substance into a liquid at a constant temperature. Let me highlight that I'm talking about thermal energy here. I usually try to avoid using the word heat. Technically, heat is only thermal energy when it's transferred from one body to another. And in this way, yes, we are adding it to the solid, but it's better to use the phrase thermal energy so that you don't start using the phrase heat in the wrong situations. So look what they've done. They've got ice around this thermal heater and they're letting any of the ice that's melted drip into our beaker. They are measuring what comes out. In this case, you can see 16.6 grams when the heater was turned off and the time interval was 10 minutes. So part 1 says state why the mass is determined when the heater is switched off. Well, we need to know how much would have naturally melted with the surroundings rather than just coming from our heater. So just how it can be determined that the ice is melting at a constant rate. Well, even though in this case we just have a total amount, we could do like the other examples I gave earlier, and I could be measuring the mass over time. And finally it says, calculate a value for the specific latent heat of fusion of ice. Now one thing I want to point out is that the amount when the heater is switched off, they did that for 10 minutes. So if I'm going to compare it with the amount of the heater when it's switched on, I'm going to need to take this value and divide by 2. Now, if I want to find my value, I need to do the amount of heat times my mass times the latent heat of fusion in this case. If I move that around, my latent heat is going to be the 18,000. Remember, that's the amount was for our 5 minutes. And our value here of 56.4. And this is going to give me 319, and that will be joules per gram. So please take another moment to read the success criteria. I hope after watching this video you can say yes to all 3 of them.